Welcome DC Circuit students. In this mini lecture we are going to use the TINA TI Circuit Simulator Transient Analysis to take a look at the voltage versus time response of a capacitor that's subject to a square wave signal. The reason we're going to do this is a great way at measuring the time constant of an RC circuit and then looking at how changing values of resistance or capacitance could change the time response of the circuit. So let's take a look at our circuit that we've drawn. In this case we have a resistor, a 12K resistor, and a 0.47 microfarad capacitor in series. And we are driving this with, I've called it the arbitrary waveform generator, which for those of you who are using Picoscope's USB oscilloscope will know that that's the onboard function generator. You could call this a function generator. And we are placing ground, our 0 point, at this point in the circuit, which is would correspond to where it would be if we were using any kind of function generator to drive this series circuit. So we're going to double click on our function generator and we're going to go under signal and we're going to hit the triple dots, which pulls up whatever we want to choose for it. This lets us choose the signal. And as you can see, we have a lot of choices. We can, and it likes to go to the other screen, we can have a single pulse. I'll be whipping this back over every time. We can have a step function, sinusoidal, offset sinusoidal, or square wave. So I'm going to select square wave, and we have an amplitude of 1 volt, and I've chosen a frequency of 20 hertz. Now that frequency was chosen deliberately with a knowledge of the time constant that we already have for the circuit. So we can get our calculator out and take a look at how this corresponds. As what we want to do is we want to choose a frequency of our applied square wave signal that will ensure that on each half pulse, each half of a period, that we'll be able to reach steady state before we switch the voltage and either start charging or discharging the capacitor depending on which direction we're looking at. So let's calculate what our time constant is. So we can do 12 times 10 to the third for our resistor times 470 times 10 to the minus 9, enter times. So we have a time constant of about 0.00564 seconds. So that's our RC, or our tau. So if we look at that and say that is going to correspond to maybe 60 some odd percent of 1/2 of the wave period, we could say, okay, let's double it and then double it again, and we should have some measure of what the total time is from that corresponds to the whole period. So let's multiply it by 4 and we get 0.022. That would be a full period. So maybe we're going to want to run our viewing period of the transient out farther, but we know we want a frequency that will give us a full period, a full waveform that takes at least maybe 0.022 seconds. So if I do an inverse of that, I get about 44. I'm going to cut that in half just to be sure, and that's going to give me my 20 hertz. So basically, if I already know what my values of resistance and capacitance are, and I know the relationship of tau to the duration of a full waveform, I can kind of zoom in on what I think the frequency would be if I want to display a full waveform of that circuit, because it's in fact the time constants that kind of sets the period of the circuit. Now I can go another step with that and I can say, well, another rule of thumb I know is that steady state is achieved in about 5 times the time constant. So 5 tau will take me to steady state. So I could redo those calculations and do 12 times 10 to the third, 470 times 10 to the 9 times, and then do times 5 for 0.0282 seconds, then double that, and get 0.0564 seconds and say, okay, if I want to make sure that on both the forward and reverse portions of my square wave one cycle, I need to make sure I allow at least 0.564 seconds for a full period. And if I express that in frequency, it's 17.7, which is, a little bit less than 20. So 20 hertz by that basis would give me pretty much steady state, pretty close to it without, having a huge long flat line on my waveform when I display it. So that's how we got the 20 hertz, is we already knew what the time constant of the circuit was. And we're using a 1 volt amplitude just because it makes the math easy. So I hit OK, OK. Now, an important thing to note, and this is analogous to what we'll measure on our protoboard circuit, we've inserted a voltage measurement point, which I've called V sub C, meaning the voltage drop over the capacitor, because that's what it's measuring. It's measuring between this point and ground, which is the voltage over our capacitor. We can do this very easily with our real circuit by just using one of our scope probes at this point, and we'll automatically be measuring between ground and this point because our scope and our waveform generator are both going to be referenced to ground. Okay, so the next task is let's display the transient. So for that we go to analysis and we go to transient, and it's going to ask us, well, how much time do you want to look? And do you want to draw the excitation voltage or just display maybe a voltage marker in your circuit? So I'm going to say let's draw the excitation voltage so we can see that square wave, and let's go to about 50 milliseconds. We can always adjust that after the fact. So okay, so as you can see, that corresponds to just about exactly 1 cycle. So you can see in green we've got our excitation, so there's our square wave, and then our we can display a legend here. So you can see that the burgundy or brown line is V sub C, which is our measured voltage over the capacitor. And so the waveform looks pretty much exactly what we would think it would. Is on our forward going waveform, the capacitor's charging, and so we have this negative exponential relationship with time. And then when we reverse the voltage, this is like the scenario that we calculated in our earlier video, where we change to a voltage source going in the same direction as the charged capacitor, and we let current flow in the other direction, and now we have this basically the opposite direction attenuating signal, and then we eventually reach almost steady state here before we switch the waveform again. So we're going to use this second half of the waveform and our calculated expressions for voltage over the capacitor to go ahead and measure the time constant from our simulated plot, and then see how it compares to what we know it needs to be, which is 12,000 times 470 times 10 to the minus 9. So to do that, we're going to do something really similar to what we'll do with our scope plotted signal, and that's use some measurement aids on different parts of our curve. So we're going to start by implementing a measurement tool here that says it'll plot the XY position of anywhere on a given curve. It's going to follow the curve. So we're going to follow our V sub C, and what we're going to want is a voltage that is predicted by our calculated expression, our derived expression for voltage over the capacitor. So we're going to go back to the calculations we did in our earlier video, and I can't write them here, but I'll just verbalize them. We had come up with an expression that said the voltage over the capacitor at any time from this point here, where the capacitor is fully charged, and we're gonna let it discharge and then charge up in the other direction. So the voltage at any point from this time is given by the amplitude of the imposed signal, which is 1 volt in this case, times -1 plus 2 times the exponent of negative t over RC, or negative t over tau. Well, we're going to take a look at the voltage that would correspond to t equals tau. So again, I'll just run through that calculation for practice. So I'm going to assume T equals tau. So my voltage over the drop over the capacitor should be my amplitude voltage, which is 1, times -1, 1 minus, times 2, times the exponent function operating on -1, or the e value raised to the -1. So I can do 1 minus enter e, which gives me 0.367 times 2 minus 1 times 1 gives me negative 0.264 volts, or 264 millivolts. So I want to know the point on my V sub C curve where the Y value corresponds to 264 M, meaning milli. In this case it's millivolts. So right now it's reading 140 millivolts. So I've got to go a little further down the curve. So 240. This is going to be a little bit rough because I'm doing it by hand. I could probably make it easier by blowing it up here a little bit. We'll be doing something really similar with the scope, so this is kind of good practice. It's good practice to use a simulator. Okay, this is reasonably close. Okay, now this value of 30.58 milliseconds isn't accurate because our zero time isn't back here, which is what that's plotting. It's this point here. So we kind of need to remind ourselves what it was that point. So we're gonna put another marker, and we're gonna position it right at what t equals 0 is for this portion of the curve that we derived, over which our expression for V sub C versus t is accurate. So that's at about 25 milliseconds. So we're going to subtract this value of time from this value of time to get the difference between B and A, which will represent the t, which should be the same as tau. That's where t equals tau. So we've now got a measured way of measuring tau. So we have 30.58 times 10 to the minus 3, because this is milli, and we'll say just what it says, 24.7 times 10 to the minus 3 minus. So we have 0.00561 seconds. So that's what we measured. Now we can check that with what we know it should be, assuming that the value of our resistor and capacitor are exactly what they said. So we have 12 times 10 to the third, 470 times 10 to the minus 9 times. So our calculated value from the exact value of the components was 0.00564. We measured on our results of our simulator 0.00561. Those are very close, and the only error in this case is my ability to position the markers and make the measurement. So one nice thing about the simulator is I don't have to worry about some plus or minus value range around my capacitor, whether or not my resistor is operating a little warm and it's not really 12K. I don't have to worry about function generator sag, although I could compensate for that by just measuring my max value. Basically, all of the errors associated with the real components has been taken away by the simulator. And the only error in measurement is just my own ability to move the markers by hand. And I could even calculate what that was because I knew I wasn't on exact positions. So that's one benefit and weakness of a simulator. So when we look at our predicted values and what we expect to get in our real circuit, we need to bear in mind that the simulator is gonna zoom in on design flaws that don't take into account real components. It allows us to not have that distraction and get a good simple idea of what's going on. It allows us to eliminate variables that we don't want to consider, but it can't see what it doesn't look for. So because we're not accounting for the fact that we could have different values of components, there is a range, a precision range, We aren't including noise. We aren't including the additional resistance or capacitance of leads. So the RC that we measure could include more than just the R and the C in our circuit. What we measure may be somewhat different from this. Now, one trick when we look at those other components is we can choose values for our deliberately selected components that are much bigger than the range of probable error. We know that any kind of long coaxial cable, such as our scope leads, is going to have a little inherent capacitance. And in fact, we have a setting on our scope leads that can help account for that. But another way to account for it is to make sure the capacitance on our circuit is significantly greater than whatever is in our scope lead. So the deliberately chosen values, the things we know more, are going to outweigh the error, the measurement error that we're never really going to know. And that's one trick to make our measurements easier and more accurate, more representative of the true values. So that is it for our simulation portion of our RC circuit time constant calculation simulation build and measure. And our fourth and final video will be the circuit build and the picoscope, USB oscilloscope, and waveform generator measurement of this same type on a real circuit. Stay tuned.